Hello to everyone over there. We are going to use a convection diffusion problem in 1D. So this is a 1D problem that we are going to solve with Seeker Fluid Soft. So this is the geometry, and the numbers and data are shown clearly in the screen. So let's draw the 1D problem. So we just draw a rectangular in 1D. So this is one that we use in this example here. Then we make it to be a complete domain. So for the sake of the demo, we just draw that. This is the length of it, about 20. 2 to 11, so about 9. We can pull it to make it 10. So that is it, about 10. We can snap the corners, make sure that they fit the size by changing the numbers here as one would wish. So that number here is fine. That x, that could be 12. That one's 12 as well. This one make it 2 and 7. And then we make sure that they are on the exact size and exact length. So that's what we have. Then by default we have two equations. So let's set up a one equation of diffusion and convection. So a 1D diffusion and convection equation, we can just take one from there and then customize it. We remove the first term, we remove that, so we have a diffusion and convection combined. So that's one equation. We're just using one element in the array. So we have one. So we have three parameters that we have to set. So that can be any mathematically valid expression. So let's define the value of SR, source term. So we call it to be minus K multiplied, and then we put a value of P over there. So we have that, and so the minus K is just a coefficient. So let's define those. This one, clear it, make it to be 1. It could be any mathematically valid expression. So we have Vx, K, P to define as parameters. So Vx, we set it up to be 0.1. P, set it up to be 1. K, set it up to be a value of 2. So that's what we have. So these are the three parameters that we have according to the demo example that we are using. So this is a 1D problem. So there is no variables along side y. Now we have to define the boundary conditions. So we specify the inlet and the outlet, and then the two sides are adiabatic. We click here, select inlet, and then put a value of 1 for the inlet. We select here, we select it to say it's outlet, outlet condition, there are two ways. This one, which is a continuity, or this one, which is also a continuity equation. But this one is a continuity at zero. This one, continuity of the derivative. So we leave it as it is. The two sides are just adiabatic. Once we have that, we go and specify the initial conditions, because we are having steady state. Initial conditions could be any number that's close to the solution. So we leave it to zero. Then we have to run. So what we do now, we compile, then we run. So the results are shown there. So we see, we can just see the numerical result behind there. So this is it. So we see the graphical results, what they show us. So it's the one is just at the beginning, and the rest are basically zeros. It's zero because we are having a source term in the system. In the equation, this is the source term, and then the source term equation is taking place. K is not set to 0. K is set to 2. So the reaction or the disappearance is so fast, we can then reduce the value of K to some lower values. So they change that, close it, then we run again. So this is another result that we get in 1D by basically changing the value of K. So we can drag our mouse around, see the values in the X direction, which are the same when we go in the Y direction, because we're dealing with 1D in the direction of X. So this is a 1D result that we get with CKFluidSoft. So we can plot these values along the X. So let's put a line and then put it there, and then put it along, so we can draw these values. So we just want to draw it along the X. So instead of length, it's better to use X. So by putting it like that, when we click, we can have 2 points along the X, or more than 2 points, 10 points, more than 10 points would be 12. So we select that, then we have the plot along the X line. So this is our solution to the problem as we get it. So we can view the values along the X as they draw. So this is actually the solution that we get from that problem, the 1D problem that we just solved inside CKFluidSoft. So thanks for your interest in using CKFluidSoft. So we will then move to the other demo.